Right, so good morning, everyone, and welcome to today's webinar. My name is Tomáš Kolarik, and I will be moderating today's session on behalf of the National Competence Center for HPC Slovakia. We are delighted to have you here for today's topic HPC and AI competition or collaboration. As we all know, the rise of artificial intelligence is changing the landscape of scientific research. Today, we will explore the relationship between classical HPC simulation and AI, whether they compete with each other or if they can work together to solve complex problems. Our distinguished speaker today is Erwin Laure, Director of the Max Planck Computing and Data Facility and Honorary Professor of the Technical University of Munich. Professor Laure is leading expert in high-performance computing and data infrastructures with extensive experience in the European HPC ecosystem. The presentation will last approximately 45 minutes. After the talk, we will have a Q&A session. Please feel free to pose your question in the chat at any time during the presentation. We will address them at the end. Alternatively, you can ask them directly to the speaker. Erwin, the floor is yours.
Thanks a lot, Thomas. Thanks a lot, everybody, for joining today and for the nice invitation to have me here in this forum. As Thomas said, I'm going to discuss a little bit the relationship of HPC and AI, where we stand, where issues are, how we can move forward. I'll do some general discussion and hopefully provide some thoughts and also give an example of what's actually going on within the Max Planck Society when it comes to HPC and AI. Well, as you all know, we basically have, since about 25 years, we have four paradigms of science, right? From empirical over theoretical, computational science, and then in the around 2000, data exploration and data in general has become a very, very important topic. Also, Jim Gray coined the term e-science for that. And in a sense, this e-science movement prepared the grounds to the next kind of evolution where we are today. And I choose the term evolution, not revolution, because I really think it is an evolution. Like e-science is an evolution of computational science. We are now in the era of AI, which is an evolution of e-science and all the computational things that we've been doing before. And there's a couple of reasons why AI, actually it started around 2010 with the deep neural networks, when it became important. And of course, since a couple of years, around 2020, with the appearance of large language models, it really got a major boost, is available today. So we have large amounts of data. There is a lot of training data out there. And the e-science since the year 2000 basically has prepared the grounds for that. And we were lucky that coincidentally, we had a very, very well-suited computational platform for this kind of work, which is this classical GPUs that are extremely well-suited and extremely powerful in the field of AI. And that allowed to build so-called killer application. It started, as I said, around 2010 with computer vision, image recognition, and these kind of things. And now with the large language models, natural language processing, and all these things are really at a boom. Yeah, ChatGPT, I think everybody of you know and is probably using. Now, we all know that AI is needing a lot of resources. And my friend Satoshi Matsuoka from Riken has plotted this graph that shows the increase of the fastest supercomputers, the classical supercomputers in the world. So this is basically this orange line here, reaching the exascale, right? and the large language model size in terms of parameters. And this is roughly corresponding to the size of compute. And this is a slide from 2023. Keep that in mind. So what he noted is that around 2023, basically large language models came to or required exascale capabilities. And the conclusions he drew from that was that now as we are exascale, and we know that basically our HPC system, they are not growing that fast anymore, right? So we go from 1, maybe 2 exaflops, but reaching hundreds of exaflops is still far beyond anybody's imagination. So he predicted that basically the development of large language models, the development of AI, will also kind of slow down because it will be resource limited. And the second conclusion he drew based on this, that we need to incorporate domain-specific knowledge into our models. I'll get back to that point, but let's stick to the first point before, saying, okay, large language models and AI has reached the requirements of the top HPC systems and thus will be resource restricted. Where are we today? So this is the currently largest HPC system in the world, El Capitan at Lawrence Livermore, with 45,000 GPUs. And if you compare that to one of the largest AI installations, which supposedly is a colossus of Elon Musk's xAI, you see the difference, right? So Colossus has 200,000 GPUs, expansions planned to 1 million GPUs, and is using 250 megawatts of energy. So it just shows that, sorry, where am I here? Yeah, AI infrastructure has not slowed down, has not stopped. It's just outperforming HPC, and it keeps outperforming HPC. It's outperforming it by at least 1 order of magnitude. And the reason is there is a lot of industry money behind that. Everybody is investing like crazy into AI, right? So you see all these announcements that the big companies are spending hundreds of billions of dollars into AI infrastructure. Data centers are being built with gigawatt performance, something that was in the HPC field not really far beyond our imagination. Right? Actually, Donald Trump has launched this project Stargate, right? With $10 billion, 5 gigawatt. And they are actually building and reinstalling nuclear power plants to actually deal with all this increase in compute power. And similar things are happening in Europe, right? We just had the expression of interest for the so-called AI gigafactories initiative, and there were 76 respondents overall, which is an enormous amount, right? Imagine this is 5 billion euros investments, and we had 76 consortia that think this is reasonable to do. Again, something that is far beyond our imagination in HPC. And even in Germany, the Schwarz Group, that's the guys behind Lidl, they announced to build 11 billion euro data center for AI, for German digital sovereignty. So there is a lot of things happening in that field that goes far beyond what is happening in HPC. Now, it comes also with a downside. This is an article from press that basically discusses how Elon's data center for Colossus is polluting the Memphis area because he's powering that enormous thing that is several hundred megawatts of power, and he's powering that with gas turbines, basically. And of course, as we are in the US, without any filters and so. So there is a big downside to that, and that's something that we have to take into account. Environment friendliness of data centers becomes an ever more urgent need to think about. But let's have a deeper look where this energy actually is going to, and again, how it compares to HPC. So there is some estimates on how much it took to train the GPT models 3 and 4, right? And it's 1.3 gigawatt hours, 1.8 gigawatt hours. If you look at El Capitan that we had before, El Capitan has 708 megawatt hours per day. So indeed, training these GPT models is at the exascale level, right? But it's doable. Yeah. So within a couple of days on El Capitan, you could probably train GPT if El Capitan was tuned towards that and before that. And even we at MPCDF, we're clearly much smaller than Lawrence Livermore, but we burn about 110 megawatt hours a day. So also within a couple of weeks, using all of our infrastructure, and if our infrastructure were tuned towards training, we could probably train it. So where's the problem, right? We always thought that training is the energy and computational intensive task, and inference then is relatively cheap. And so what? Well, indeed, it is relatively cheap. So there is not a clear number on how much a ChatGPT query really costs, but assumptions are from 0.3, which is more or less equivalent to a previous Google query, to 20 watt hours. 20 watt hours, of course, is 2 orders of magnitude more, right, than a typical old style Google query. So again, this number in isolation is not a lot. But if you think about how many ChatGPT queries are there, they are estimated to burn about 850 megawatt hours a day. So that means El Capitan itself is not enough to serve only what is being done in ChatGPT. And if you take all generative AI research requests together, we are at an estimate of over 40 gigawatt hours a day. So it is really these search requests that are the expensive one and that burn all the energy and need the huge computational power. So does this mean is there huge computational infrastructure, huge computational power now clearly is in AI? Is AI taking over HPC? So is there still a kind of competition, or can there be collaboration? Well, in a sense, if you look from a high level, AI can have many roles in scientific research, many roles in where we typically employ HPC today. You could use surrogate models to do optimizations, augmented simulations, parameter search. You can use foundational models helping with writing, getting a kind of co-pilot question and answer machine and so forth. You could even develop scientific codes, AI helping debugging, encoding, and optimization, code codes, and so forth. You use AI in controlling complex systems, simulation, digital twins. You use AI in design optimizations, like materials design, biological design, proteins, devices, and so forth. And ultimately, right, if there were artificial general intelligence, you could think of an artificial general intelligence scientist where artificial intelligence does everything, right? Poses the scientific question, develops a plan for experiments and simulation, performs the simulation, writes up the paper, and that's it. And so we have nothing to do. We can go to the beach and watch AI doing our work. But where are we then really today with this? It's actually really, really surprising how well AI is capable of dealing with complex problems today. So this is some latest benchmarks using GPT-4.1. So that's GPT with the reasoning models involved that allow a chain of thought approach. And so this benchmark has shown that GPT-4.1 is actually on par in math with the top 500 US high school students. And in programming, it's in the 86th percentile of programmers. So AI has today really impressive capabilities of what can be done. Now, as we said before, the workhorse of AI is GPUs. Yeah, I put here a picture of the Grace Hopper chip, the current NVIDIA super chip. And these chips are actually also driving HPC. Right? The largest HPC systems are equipped with GPUs. There was the recent opening of Jupiter, the first European exascale system that is equipped precisely with these Grace Hopper chips. And there are only two kind of legacy non-accelerated systems in the top 300, Fugaku in Japan, and they recently announced that we'll partner with NVIDIA to build the follow-up system, so it will have GPUs, and the Taihu Light system in China. And by now, about half, or even probably, this is old numbers, the latest lists, probably more than half of the systems in the top 500 are accelerated. So we are building on the same foundation, means should be very well suited for collaboration. But we need to look a little bit into the details. Yeah. Classical HPC, classical simulation modeling needs typically high precision. So most of our codes are in double precision FP64. AI, on the other hand, does not need high precision. So they are happy, most cases, with FP16. And you see, for inference, FP8, FP4 even mentioned. Yeah. So this chart shows the performance development of an NVIDIA chip, of NVIDIA GPUs in FP64, which is the blue line, and FP16, right? So that's half precision. And you see that we only get a very, very modest increase in FP64, while AI capabilities, since around 2020, is exploding. And it gets even worse if you look at tensor performance. Yeah. So that gives another boost to low precision computation, and is particularly well suited for AI, but I haven't come across really any scientific application that uses the tensor cores. So there is competition. And the first problem we are facing is the rising prices of GPUs. So this shows the GPU prices of NVIDIA, and you see the steep increase from the A100, right? So that was the time before 2020 when we were talking roughly $10,000 per GPU, going up to the H100, 200, and Blackwells, and we are approaching $35,000, maybe even $40,000 these days for Blackwells. And the following systems, the Rubin systems, are expected to maybe even double that price again. And remember what performance we get for this price. Yeah. So you see the same increase in AI performance. So this is good, but we are paying 3 times, 4 times the price than 10, 15 years ago for a performance that has not much increased. So that's a real problem for HPC. There comes other problems, and that is reduced availability due to big buyers. HPC systems have, the typical one in the mid-scale that we at MPCDF are operating, and perhaps you in Slovakia operating. They have a bunch of 100 GPUs, maybe 1,000 GPUs. High-end systems have tens of thousands of GPUs. The big buyers are buying hundreds of thousands, millions of GPUs, right? So when you knock on NVIDIA's door and say, hey, I want to buy 500 GPUs, they don't notice you anymore. It's in the noise. And the other thing that might affect us, and for some time, for some point in time, has actually affected us, is also regulations. There is a big fight on supremacy in AI. And for some time, the US has actually limited the sales of GPUs to some European countries. Austria, where I'm from, and also Slovenia, Slovakia, have been affected by that. That was only recently lifted, but there's sure further AI regulations are likely to come and will make our life difficult. But there's also the technical competition, as I already explained. HPC is not driving the chip market. AI is, right? Our requirements and our market is simply too small. And it actually has always been that case, right? HPC was always riding the wave of mass market chip development over the past decades, and has not the economic power to actually drive it. And we were lucky enough that the mass market and HPC were pretty much compatible. But now with AI, it's not that compatible anymore, right? We are losing FP64 performance. Focus is really on lower performance. So yes, you can still argue that AI is essentially HPC, right? But this doesn't buy us anything for the classical simulation and modeling workloads. So what are we going to do? On the one hand, we probably should adopt. That's what we've always been doing in HPC. So we need to think about lowering precision. We need to think about mixed precision, not using FP64 everywhere. We need to be thinking about emulation, like the Osaki scheme, where with lower precision you can emulate higher precision. But there's also thoughts out there to build our own chips, right? Chiplet technology that is being used, for instance, in the current AMD chips, gives us a means to more easily design and develop our own chiplets and put them on a substrate for the packaging. So there is this open chiplet vision where you basically can just plug and play different chiplets on the substrate. This is still in very, very early design, I would say. There is no standardization yet, so it's not really clear how to interface the chiplet with the platform. And I haven't seen any concrete proof of concept neither, where this has actually been put into practice and shown to work. There is other things coming up. non-von Neumann computing approaches like quantum and neuromorphic. They are also all still into very early stages, and I don't expect them to become mainstream in the next couple of years. But what is already clear is they are likely only useful for very specific use cases and most likely also not that useful for classical FP64 numerics. So remains to be seen what's going on there. But I want to just give you a little example on some work we've been doing on mixed precision. So that's a fusor plasma simulation with a code named Gene that is being developed at the Institute for Plasma Physics at the Max Planck Society. And the chart you're seeing here is showing the total energy profile over time. And that's the double precision simulation, so that ground truth. And as this is turbulence, we are not about to really match the, as you see, quite turbulent line here, but the important point is the average that you are getting. And here you see the same simulation with different precision profiles. And as you see, it looks very similar, and you get the same average. So it means that yes, indeed, you can use lower precision for that. And how far you can go depends on the terms. So this is a simulation doing predicting the error with lower precision. So on the y-axis, you have the error. On the x-axis, you have the precision, and so then different terms in this gene simulation, right? And basically, you can see, so this is B float 16, this is FP16 precision. For many terms, this works out fine. Some terms, if you go below 7 bits for the precision, below 4 bits, then the error explodes. But others are pretty insensitive to that. So there is a huge potential in mixed precision, but unfortunately, it's very problem dependent. So you basically have to test it out for each application and each problem. And that's very tedious and time consuming. So let's look now really at the collaboration on a high level where people see really a means for AI and the role for AI to enhance science and potentially also HPC. So there are different motives and different ways on how you can, or people are actually including AI into their scientific workflows. So on the one hand, there is steering, so you have your HPC simulation running and AI might interpret the results, perhaps with the human in the loop, and steer the simulation. You can have inverse design where both HPC and experiments are working together. So AI is interpreting data from experiments and guides the simulation with them. You can have multi-stage pipelines where, based on some results, AI triggers other simulations, and eventually the kind of digital twin model where HPC and AI work together very closely. And I try to give you now some example of what's going on within the Max Planck Society and in our center in these ways of combining HPC and AI and embedding AI in scientific workflows. So one of the big examples of AI usage in science is clearly AlphaFold, which was one of the first killer application in the protein folding, right? That works very well and much better than any other simulations that we had been doing before. Clearly, image segmentation is another, I would say by now, classical field where AI methods are being used a lot, but it's being used in high energy physics for particle track reconstruction, for mapping the clouds on the Milky Way. And for instance, we're also using it to generate synthetic images for training MRI data. Reason is you simply don't have that many brain scans available, yeah, that you can reasonably train the models. So you need to first generate images that you can train it. There is a lot on retrieval augmented generation. We'll give you some examples on that. GANs is being used for chemical structure generation. Material science, you recognize crystal structures. Again, this is a kind of imaging use case, but also you use surrogate models for error corrections and so forth. So one thing that many researchers and many field pilots, so there's an example from geo and anthropological research, where you basically feed the research papers that you have in the field into a model. You fine-tune a smaller model. In this case, they use Llama 3, and build a co-pilot that you can interact with, ask questions, get answers, get inspiration on your research directions, and so forth. So that's being used in many different fields, not only in geoanthropology research. Earth system science is a field where a lot of AI is being used. You have the foundational models for the weather models. You use diffusion and diagnostic models, hybrid models, and eventually build really a kind of digital twin. There is this Destination Earth project, for instance, right, that tries to build the digital twin of that. And AI is being used a lot there. And you might have heard that, for instance, the weather forecasts that ECMWF is giving out every day today actually are coming from AI and not anymore from their simulation models. AI is being used in material science, in the feedback loop, the example I've been showing before in practice. So you use AI to fine-tune experimental parameters. So you do your experiments, you collect the images, you do an analysis, the AI agent is fine-tuning the experiment, and you repeat the experiment. MRI imaging I've already discussed, so there's a lot of work going on that. And I think also very important, there is work on AI methods itself, particularly more efficient methods. So there is a lot of potential to improve the training and also inference, as we've seen before. These are really the very, very costly things in AI. And if we can be more efficient and get the computational complexity down for training and inference, it will have a lot of impact. But AI is a subject of research itself. So it's not only researching the methods or employing the methods in scientific workflows, but also thinking, how is AI actually influencing science? How is AI influencing society? Yeah. So AI is influencing our culture. We see it every day. And so clearly this is also a line of research in the humanities to figure out how that's actually being done, how our new interaction patterns with AI are developing, and how AI is influencing and changing society at large. So there was a very interesting experiment earlier this year by DOE, where several DOE centers brought together over 1,500 researchers from all different scientific domains in a so-called AI jam session. So they put them together in huge rooms, as you can see here, and exposed them with AI, and they were tracking what people actually did with AI, how they interfaced with it, how they embedded AI into their scientific workflow. So they were really doing their normal scientific work, but trying to fit AI into their models. So that was a very interesting experiment. Unfortunately, the results are not public. That's a model that I think we in Europe should think of and try to do something similar at time to really understand how AI is influencing science and what people are doing in a more structured way than just a kind of anecdotal thing like I've been doing now, just giving you anecdotal evidence of how AI is being used today. And I want to finish my talk by just giving you some feedback from a recent meeting, worldwide meeting. You see some probably faces around here from Europe and Japan. That was in Japan for this international post-exascale project. So discussing what comes post-exascale, and AI, of course, was the big topic. And so the conclusions were in the kind of summary was in a couple of different angles. First was the future of AI and HPC architectures, something that I've been discussing a lot in this talk already. So basically the conclusion was hardware is vendor driven. We have to invest in the software. So again, emulation, perhaps chiplets, but we probably need to rethink our numerics and see if we can do something more intelligently. There was a lot of discussion on AI in code generation, programming. So one hypothesis was you don't need to train people in coding anymore. You need to train people in prompting. We felt maybe it's also because we are old. We felt that there's still a need to understand coding, and just prompting and let AI do is risky. Yeah. Also, you need to put a lot of effort into validation and seeing it's correct. So we think AI can be a wonderful tool for experienced developers, but it's not replacing education in coding in the first place. And what current AI still lacks is intuition, right? So there is still a need for all these things to be scientist guided. A lot of discussion was on data curation and generation. AI is building on data, right? And without data, there would be no AI. So we need to think on how can we build trusted repositories of data. Can we actually do in situ AI processing with intermediate data before it's being discarded? On the supercomputers already, we need to think of our workflows. So how can we train the models? How can we use the data and so forth? And finally, we see all these things on AI is improving the scientific process. So this is all nice, but is it really improving it? How are we measuring that, right? That's the general problem. If you have a new tool, eventually you want to measure it by saying, okay, things are being faster, but how to measure that is difficult. But clearly, Gen AI is very good at supporting tedious, repetitive tasks, literature review, hypothesis generation, code maintenance. So this is very good. It's very good in data-rich domains, like in protein folding, astrophysics, or in domains where first principles fall short in the first place. But we need to be very careful about biasing. So it's still a lot of work on that. And as I said, this global collaboration, this 1,000 Scientists Jam, was a kind of real example on how we can move forward. So as a summary, I believe AI is here to stay. So we're still at the beginning of the hype, and we don't know whether it is really only a hype. It will slow down, but all indications are it's definitely here to stay, and it is a new ingredient in our scientific toolbox. The impact is still somewhat open, but it has great potential. And as in HPC, we're clearly facing the issue that the hardware market is driven by AI, and we have to respond to that. And that makes our life at HPC data centers a little bit misery for the moment. But we'll see how things will evolve there. Okay, with this, I'm at the end. I'm happy to answer any questions. Thank you very much.
All right, thank you, Erwin. That was a very interesting and comprehensive presentation. Thank you for sharing your perspective on these important trends and also for sharing information about your work and work of your colleagues at Max Planck Society. So I'm now opening the floor for the questions. If there are any questions, please go ahead. You can write them to the chat section or ask them directly to the speaker, to Erwin. Okay, so maybe you need more time. So if I may, I would like to ask the first question. In scientific communities, there is often a debate about the black box nature of AI versus the mathematical clarity of classical simulations. Do you think the trust in AI results is still a major barrier for scientists?
It is well, yes and no. So I think I'm going back to this you said before, that the validation is the important thing. So scientists are happy to work with a black box to some extent, but they need to be able to verify the results. Many scientists see actually AI kind of like a first grade student, right? You give them a task and they come back with results. How much do you trust that they have really done the right thing? So there is a need for validation. In general, the black box approach is fine and being accepted, but people do understand that you need validation.
Of course, thank you very much. I'm interested, for example, in the changes in European Center for Medium Range Weather Forecasts, because they decided to use AI. They, in my view, might not be able to learn because they don't see and understand how they did their forecasts. You know, if they use classical computation, classical modeling, then they're able to see how they got their predictions and why they maybe have failed if they failed. So this is yeah. Please go ahead.
I'm not too deep into that. I just followed the recent talk from ECMWF people. But clearly, they are not giving up their simulation models neither. So they're still running them, and I guess they're still using them to some extent to validate the AI results. But how deep they go there and how the workflow really is, I don't know. So I would actually be interested in a similar talk from an ECMWF person and figuring out how to do that. Maybe it's a good good thing for a future talk in your seminar series here.
Okay, thank you. There's one question in the chat. Lubomir, thanks you for the great presentation. presentation. Would you like to read it for yourself? I can read it aloud for you if you want.
Yeah, it's okay. It's about the hallucination. Yes. This is a big concern, and I think this is one of the topics where more research in AI methods itself are needed to get better accuracy in the results, to get less hallucination. At the moment, this is, as you said here, it's limiting uptake. So I think it's an ongoing and certainly a very important topic of research in AI methods itself.
Okay, thank you very much. Are there any other questions for Erwin? If not, I would like to ask one more question. From your perspective, is there any specific area where you think AI is currently overestimated? And now I understand that you, as far as I understood, you call for collaboration, but maybe there is a specific area where it is really overestimated and should not be, and doesn't have the value we expect it has.
Yeah. It's a difficult question, of course. I think people start to understand that AI is a tool in the toolbox that they need to use in conjunction with other tools, but it's not the only tool. So I think those projections that AI will take over everything, they have so far not come real, and people who were thinking along that line are getting back and say, no, there is still a need for first principle simulations and the like. I can't really point out a specific domain or problem where that happened. It's more the kind of general approach people are taking that. But it's in a sense following the normal hype curve, right? So you go up the hype curve and then you get disillusioned, and then you find a way where technology really has a value. And I think we are still, to some extent, on the rising curve. Yeah, we haven't found the peak on this hype curve yet. But I haven't found a community yet that has, for instance, abandoned AI. It's not the case. They're still all investing in it.
Okay, thank you very much. So, if there are not more questions for Erwin, then it seems that we have covered all the questions, and I would like to thank you once again, Erwin, for your time and for joining us today. It was a pleasure to have you, and a big thank you to all for participants for being here and for your active engagement, especially to Mr. Sintala. Before we close, I would like to invite you to our next webinar. Today, we discuss the collaboration between HPC and AI. In our next section, we will look at the concrete example of how Europe is building its own open AI models using this infrastructure. The webinar is titled Building Europe's Sovereign AI, the Bielik AI Case. It will take place on December 11th at 10 a.m. Our guest speaker will be Katarina Staroslavska, I'm sorry if I mispronounce her name, who will present the story of Bielik AI, a family of open community-driven AI models developed in Poland. You can find more details and registration links on our website. We hope to see you there. Have a great day, everyone.
Thank you very much.
Bye.
Bye-bye.